Hi, I'll be talking today a little bit about my work related to applications of category theory in particular in the domain of robotics and automated planning. And then I'll be motivating this talk around this notion of contextual attention, which is a term that I defined for this area, and I'll provide some more definitions as we go on. So this talk is broken up into 3 parts. The meat of the talk is really the middle part. I'll be taking a tour of some of the work that I've done related to applying category theory in some robotic contexts. And in particular, the third part of the middle chunk of this talk will be related to the formalization of this notion of contextual attention. Okay, so the motivation or the background of the problem that I'm after is related to making use of context in robotics. Context awareness is a term that's used in a variety of different subdomains within robotics and mobile devices and IoT device research. But it basically refers to the mechanism that allows an agent to adjust its behavior in response to some dynamic context information, primarily related to the location and resources when we're talking about mobile and IoT devices. But in the domain of robotics, there's a couple of different ways context can emerge, and it really emerges through this increased availability and capability of sensors that are being attached to these systems because they're gathering. You might have some LiDAR sensor, you might have an image sensor, ultrasound, force sensors. And all of these things are providing some notion of knowledge about the world and the scene in which it's operating in. And so managing this context needs to be done in an efficient way, and choosing what's relevant context based on what you need to accomplish is imperative, because as the availability and capability of these sensors grow, this increases the computational demands because more algorithms are making use of this information and kind of casting them out to be important knowledge. And also deciding what information is relevant makes this knowledge interoperable between tasks. Because effectively what we could do is say that we have a bunch of information about our context, but really only a small subset is relevant to our actual task at hand. We don't have to completely drop all that information. We might want to put that in like hot versus cold storage, which means that we can make it more accessible or not as accessible in terms of our accessing of that information. And we can make decisions better that way if we can have an understanding of what context is important. And so what I'm interested in is a general framework for determining what is contextually important, and I'm terming this as contextual attention. So just some terminology here, just so that we can have some common ground in terms of when I use the words context, action, task plan. So context I'm referring to is the description of the characteristics of the environment an agent must act in. And so it's the description of the characteristics of the environment. So it's a chosen syntax in which we describe the characteristics of the environment instead of just the environment as it is. An action is an operation that changes the state of some or all characteristics of that environment. And a task plan is a sequence of actions that achieves a specified goal. And so lastly, all of these pieces build up to this definition of contextual attention, which is the identification of context entities that are most important in achieving the task plan. And in my scenario, I'm saying importance means that some property of achievable tasks exceeds a given threshold or some notion of a threshold when that context entity is removed or modified. And so I'll show a little bit of an example just to give you some more intuition. But before I do that, I want to make a brief comment about related methods for contextual attention, or things that might sound like contextual attention within the domain of AI and machine learning. And so in perception and sensor fusion, the word attention is used very often, but it's referring to a mechanism within the deep neural networks that are trying to pay attention to context within an image. Oftentimes it's in the domain of image processing and computer vision. And so what that means is that it's using the context to determine what is occluded from an image or fill in the gaps. Another way that someone might approach this problem of contextual attention and finding the most important representation is representation learning, which is leveraged within reinforcement learning. And so the goal of representation learning is to identify algorithms that can synthesize and find the most concise state representation that is going to be most useful in deciding the next action. And then the some third example in perception and sensor fusion is this notion of value of information analysis. This is more of a kind of philosophical term in that it's this aim to identify how to evaluate how important information is by running experiments and seeing if I were to run that experiment or if I were to gather that measurement, how much of an effect that would have on the algorithm. Okay, so then in the domain of knowledge representation and planning, some people might see contextual attention appear in these three terms or domains, which would be case-based reasoning, which is also kind of a philosophical perspective, which says that can I use my old situation to inform how to, the old situation and a new situation, and identify the difference between them, and then use that difference to inform what my next action should be. So kind of deriving the next action based on a difference between old and new. There's also notions of recommender systems. We've all been exposed to them through YouTube and Google search. But basically, they have some notion of attention or importance because they are giving you content that is most relevant based on your previous searches. And then there's this notion of Bayesian networks, POMDPs and MDPs, which basically is the baking in of contextual importance into your reasoning. And so what I think are the limitations in these practices are that most of these are data-driven, if not philosophical, and it requires, some amount of learning and some history, and it also, in some scenarios, it also requires attention criteria a priori, so kind of baking in what's important about the environment that you're in is either built into the machine learning model, or it's kind of hand-weighted, similar to how you would use a Bayesian network. There's also an emphasis on inferring high-level context from low-level context. That seems to be the bulk of the work when it relates to context reasoning. So basically what people are after is given some low-level information like sensor readings, how do we synthesize all of that and put it together and infer some sort of high-level context. And another thing is that there's not much effort towards defining denotational semantics for these relationships, contextual relationships. And I think the last thing and I find most important, is that they're not tied to capability of the agent. So context, I think, is best defined in conjunction with knowledge about what the agent is capable of, because context determines what is most important. If a robot can't actually execute move action, so then location really won't matter. Okay, so I'm just going to walk through an example scenario so that you can see a little bit about what my intuition about context is. So what we have here on the left is, let's say that it's a knowledge graph, and we have some data inside of it. So each of these little boxes refers to some data entity, and then the arrows are just relationships between them. This is just an informal depiction of a knowledge graph. But basically, this knowledge graph tells me that there is a civilian at a particular location on University Avenue, and it's adjacent to a Dunkin' Donuts. We also know that this civilian has a home address, and we also know that their home has a granite countertop, and they're 26. And so this information we're kind of given all this information up front. However, only some of this information will be relevant for completing the task. So if I were to remove the gray boxes or delete it from this graph, it wouldn't really impact my ability to accomplish the task of going to an injured civilian. So say that my skills within my agent have the ability to move forward, move right, locate the civilian. All of these tasks are achievable with what the agent is equipped with. But by removing the information such as whether she or he has a granite countertop, really doesn't affect my ability to accomplish the task. However, if my agent is equipped with different things, like the ability to identify, measure surfaces, remove surfaces, and basically do what you need to do home renovation, then there are certain scenarios, some of this knowledge is relevant, and in particular, the knowledge about the granite countertop suddenly becomes relevant. So there's, it seems to me that there is this relationship between some system that's tracking changes in the context and some system tracking the tasks that are achievable. And then I propose that there's some structure preserving relationship between them that can be formalized. And just to ground everyone a little bit further, when I refer to context and task plan in robotics, I'm referring to things like ontologies and first order predicate logic to describe different aspects of the context. And some example semantics that are currently leveraged within the robotics domain are formats like URDF, SDF, and NOROB. And then when I refer to task plans, I think that some common syntax are these hierarchical task nets, Markov decision processes, directed DAG, or bipartite directed DAGs. And then some semantics are things like strips and PDDL. So what we're after then is if I wanted to start formalizing this relationship further, I'm thinking about all of the requirements that I need to have in my formal semantic framework so that it can encode all of this information. And then if we're keeping in mind what the syntax and semantics are for task plans and context, we'll see that we need this ability to encode procedural data because task plans have some notion of sequence and temporal aspects to them. And then we also need this ability to encode data because knowledge is kind of made declarative and not necessarily follows this procedural paradigm. We also want the ability to encode these structure preserving relationships, which is the primary purpose of the modeling between task plans and context. We also want the ability to describe composite and composition relationships. Composites are relating the parts to the whole. It refers to how to decompose things. And composition refers to how things can be merged, glued, or synthesized. And both of these domains, task plans and context, have notions within their semantics about decomposition of things, how do we relate subparts into their parent parts. And then they also have this notion of merging or combining tasks in the case of task plans, or combining knowledge in the case of context. So those things are going to be important things to model. I think it's important to encode these binary relations such as equivalence and inclusion, which so that we can make statements about whether two things are equal or if there's some subpart or kind of subset like behavior or relationship between two things. And then lastly, we also want to have it be flexible enough to encode constraints demanded by the semantics of the task plan, the context and task plan. And so some example constraints would be something related to the domain that are not explicitly modeled using this framework, but we kind of want to add that as an important relation based on our knowledge about the world. And so so this is kind of the rubric in which I'm evaluating myself against identifying a semantic framework and relating task plans and context. And I'm saying that if it's successful, then we can use this formal to simulate the effect changes in context have on a robot's task capabilities. So I just want to seat this within the literature. I think that this is model-based systems engineering and robotics and category. In particular, the robotics subdomains are things like knowledge representation and AI reasoning. And so a lot of the work that's related to this sort of model transition and model synchronization is really inspired by the intersection between model-based systems engineering and category theory. And I'll be talking a little bit about delta lenses, which was proposed by Zinovy Diskin. Okay, so that kind of lays the groundwork in terms of the problem and the motivation. And so now I'm going to go into a little bit of a tour of some of these applications, starting from the bottom, and the bottom being like fundamentally what is a category if we want to choose to model all of these things using categorical semantics. And then I'll talk a little bit about functors and their importance and some examples of application. And then lastly, I'll build up into the definition of lenses and C-sets for contextual attention. Okay, so the branch of mathematics that I'm attempting to leverage within this, through this formalization is category theory. And it's a branch that provides mathematical structures whose properties are attentive to composition of relationships. And so to begin defining a category, the first thing that you'll need is objects. And then those objects have some relationship between them, and those are denoted as morphisms between objects. And then those morphisms there should be a definition of a composition operator, which tells you how you will compose morphisms together. And the only requirement of this operator is the fact that the of your morphism or your arrow should be the same as the source of your second arrow in which you're composing with. And so these are the fundamental ingredients of defining a category. So any sort of modeling that you do using categories, it has to be done by first identifying what your objects are, identifying your relationships, and then figuring out if they compose or if they have some sort of compositional behavior. Okay, so this is a basic ingredient. Now what we can do within category theory, and there's a broad body of work that is expanding this definition of category to include a little bit more specific axioms. We can start extending this definition to add the addition, or include the addition of what's called a tensor product. And this tensor product should behave nicely according to associativity and braiding. And so this extension of a category is called a symmetric monodal category. It's not so important that the naming is, you kind of grasp the naming right away. The most important part is that the tensor product is another operator in which you can start combining things and define you can define the joining of two objects and also the running of morphisms in parallel. This kind of gives you this two-dimensional ability to your modeling. And then the other benefit is that the community has developed a graphical syntax for symmetric monodal categories, which is called string diagrams. And string diagrams are defined by boxes and strings. And you can see on the bottom right, there's an example of a string diagram. Basically, this is encoding the composition of f prime and g prime. So you read this from top down, and you can see that as input to f prime, you have the tensor product of a and b. And then the output of f prime is the tensor product of b and y. And then following that, you have this other arrow, which takes the tensor product of b and y and returns the tensor product of c, a, and b. So these are just some example definitions within category theory, but the most important part is that these can be used to model aspects and behaviors that you might observe in the real world. So one example of that is within automated planning. And so this is a picture of something that you may have drawn before, which is this relationship between two actions, and maybe there's information that is making two actions dependent on one another. And you might draw this as boxes and connect them in this way. But as we just saw on the previous slide, this can be described in more than just a picture. We can have some formal definitions related to it. So if we were to take an example, like the planning domain definition language and some semantics from automated planning, we can start naming or kind of assigning these parts of the definition to concepts we find in automated planning. So this can include, so first what we need is objects. And so we define objects as being precondition and postcondition or and effect literals. And the morphisms are actions that take these precondition literals and return effect literals. We can define composition as the chaining of actions. And then we can take the tensor product to mean that we can have parallel actions or the conjunction of literals. So if we were to take an example where we wanted to chain move, pick, move, drop, so we can assume that maybe this is like a pick and place task, we can compose the actions in this order: move, pick, move, drop. And then the benefit of having this formal syntax in the background is that we can start taking slices, horizontal slices of this diagram and making some expression out of them to say what objects are being tensored together and what objects with what arrows are being tensored together and what arrows might be tensored together. And so the benefit that this might have is that, say you have a dynamic system and you want to track how your process is progressing over time, you can use this sort of sliding effect from top down to say, well, at time t2, I have knowledge of these certain literals, the conjunction of these literals, and maybe at time t7, I'm executing the drop action in conjunction with knowledge about these other literals. So this basically gives you some ability to know what sort of resources are available at a given time and potentially what action is being executed at that time. And so that was just a demonstration of some of the work presented at the ICHCAI Generalization and Planning Workshop. So if you want more information, you can take a look at this paper. Okay, so we talked about categories, and we talked about some extension of the categories. But then there's also this ability to relate two categories together, and that can be done through functors. So what is a functor? So there's two representations of the definition, or one. Well, there's a written definition, and then there's an example, just to illustrate what how the functors actually work. But essentially, they can be thought of as being structured preserving maps between categories, and the primary structure within the basic definition of a category is composition. So essentially, a functor between two categories that have no more additional structure must preserve composition. And they should adhere to two axioms, which is that it should relate the unit object in one category to the unit in the other category, and it should preserve composition, as I said. So what we can do is go through and see an example on the right to say that, say we have two categories, X and Y, and X has objects arbitrarily named A, B, C, D, and some arrows between these objects, and I call them F, G, and H. I have another category, completely unrelated, and I didn't even know X existed, but I have another category where my objects now are dog, cat, mouse, and rabbit. And then I want this category to model what chases after what. So my arrows say that my dog chases after the cat, G prime arrow says the cat chases the mouse, and the cat also chases the rabbit. And so I have these two distinct categories, and I want to form a relationship between them. Well, I can propose a possible functor, and the functor should assign objects to objects and arrows to arrows. So I propose that my functor will send A, B, C, D to dog, cat, mouse, rabbit. This is probably the most obvious choice. And then I also propose that F gets sent to F prime, G to G prime, H to H prime, and the identity morphisms get mapped accordingly. And so the most important thing to check here, because we've also validated that our functor is actually sending the identity morphisms appropriately, the most important thing to check here is that composition is preserved. So if I have F composed with G, denoted on the bottom here, just take note of the order in which they're appearing in this operator, but effectively this means F first, run F G. So if we run F first, we have something from A to B, and then we run G again, G, then we have something from B to C. So now the target of this arrow is C, and F of C is mouse. And so we can kind of execute the same process here in each of these equations, And what we'd validate is that the composition is preserved. Okay, so that's the notion of a functor. And so the value of it probably you're beginning to see what kind of value a functor might have. And so one example in which we can leverage functors is in compilation, from formal compilation. And for this project, what we were interested in was the fact that there exist 2 robot vendors within a potentially small to medium manufacturer size. And it's often the fact that these, and when you want to reprogram one of these robots, you have to go to the vendor and hire someone with specific skills in order to program this new robot. You have to do the same once you switch out the robots. So how might we want to go about reprogramming these robots when we only have knowledge about these high-level behaviors? So basically, how do we compile down from this goal-oriented description of our program into specific robot controller languages so that we don't have to keep hiring specialists or having to reprogram something every time? So this was the sort of motivational framework for what we had executed within this goal-oriented robot programming project. And effectively, we had three domains in which we were trying to model. We had this notion of the physical domain, which is the physical resources in which the robot was behaving on, like a door or a block. And those things exist in the real world. And then we had this notion of software, so this sort of abstracted software layer, which encoded the ability to move to the door, open it up, and release the door, and then move to its original position. And then that needed to be related to some sort of low-level specification, which was described by the robot vendor. So we wanted to relate these 3 layers together. Our initial approach was to just make everything a symmetric monodal category and then assign or describe or define functors between all of these categories. And then, assuming that composition is preserved, then when we take composition of arrows in one domain, then we should be able to construct a composition of arrows in the other domain. And this was done a little bit more informally in that we didn't have a framework that was validating the fact that these properties needed to be preserved. But the spirit of it was implemented within our robotic programming framework. So essentially, once all someone had to do was take a look at our skill library and say, I want to use these skills, skill A, B, and C in parallel. And once we've described that program in that high-level language, then the mappings would be able to determine what sequence of low-level controller languages statements would be able to execute that high-level goal. And so this was also joint work with Siemens and the Advanced Robotics for Manufacturing agency. And if you want to find more information about this work, you can take a look at this paper. Okay, so this kind of builds up into more complex structures, which we'll find in the lenses NC sets. So now that we've taken a little detour, let's bring it back to this sort of contextual attention view. And I said in the beginning that there's this context, and then there's also this idea of achievable tasks, and there are systems that have their own internal structure, and I want to relate them together. So now I have to be a little bit more specific about what I want. I need to figure out what those things are, these little dots and these arrows. I also need to figure out how the composition behaves in this guy. And then I have to do the same for the other side. And then lastly, I have to figure out what kind of constraints need to be imposed on this map so that they can relate them together. So when I think about this problem, I think, okay, I need something that's like context data-y. I need to also encode changes in context. I also want to figure out, well, what does it mean to compose these changes? And then on the other side, for the other system, I need this notion of space of task plans. something that's changing in the space of task, or changes to the space of task plans, and then what does it mean to compose these changes. And then I have this vague idea that there's a synchronization map happening. So at the onset, I'm proposing some of these structures to be what I'm using to model this information. So context data can be done using co-presheaves, and the changes in context data are managed by the spans of co-presheaves, and I'll provide more definition or more details in the coming slides. But the composition of changes is done through pullback of these spans. And to the right, the system tracking achievable tasks. The space of tasks can be thought of maybe as a monoidal category, similar to what I was thinking about in automated planning. The change in space of task plans is these spans of monoidal functors, and the composition of changes is the pullback of monoidal functors. And then lastly, probably the most important decision I'd have to make is what kind of synchronization map exists between them, and I'm suggesting a discrete op vibration might do what I need to do. So it turns out that this was actually executed and defined by Zinovy Diskin within the definition of delta lenses. And so a delta lens is a morphism in the category of small categories. And then where the arrow or the morphism is a discrete op vibration functor. And so what I'm suggesting is that one of the categories be task plans and the other be context. And then I'll provide more definition on the details of those categories. But at a high level, the delta lens works such that if there's an arrow that exists within the category of context, which is this B on the bottom, then there must exist a unique arrow in the category of task plans, and such that when the functor is applied to this arrow, it should map to the arrow in the context, the category of context B. And then the lifting, this is called the lifting property, and the lifting should respect composition and identities. So this is this is at the high level, this relationship between task and context. And now if we zoom in to look at one of these categories, I also want to say that these categories follow this structure where the objects are more abstractly models, and the arrows are model updates, and updates represented by deltas or spans. To the right here, this is an arrow between L and R. And the arrow is demonstrated by this span where the apex is some shared information between L and R. And then these maps are they're capturing difference in a way because they're aligning what is within A into the objects L and R. So in this gray box, it's saying how does A and B look inside? And then to the left, the delta lens is describing how are A and B related. And the reason that I like this particular model is that it has some nice modeling capabilities which I like, which is this traceability between task plans and context, the ability to encode change information via these spans, and the synthesis of space of task plans using the lifting property. So being able to identify this unique map to this new changed version of the space of task plans is probably the most important aspect of this. Because in this way, if there's an error that exists within my context, then I can lazily evaluate the next change, the change to the space of task plans using this lifting property. Okay, so to go into a little more detail, the category of context I'm saying is a category of co-presheaves where the arrows are spans. And what a co-presheave is that there's some OLOG category or schema category, which is a syntactic category for databases, where the objects are types and arrows are ISA relationships and properties. So you might traditionally think of this as an ontology, where the nodes of your ontology are the objects in this category, and then the relations outside of those nodes are arrows in the category. And then there's assignment of data into each of these, or and the assignment of data, which is this functor into set. And so all of my objects are these co-presheaves, and the arrows then become the spans between co-presheaves, where the apex is some common value or common entities between two database instances. And then the composition of these arrows are pullbacks. So to show a little example here, my context for, let's say that my ontology is saying that there's an agent, an action, an object, and that object has the location. To the right is some instantiation of that information, where I have a robot that participates in picking up a cup that's in the sink, and to the right of my span, this triangle here on the right bottom corner, it says almost the same information except the cup is on the table. So the apex is this. It demonstrates that there's these common entities within or between these two database instances, and it's that the robot is picking up a cup. So that captures some of the kind of the change information that's happening between these two database instances. Okay, so then I want to relate this category to this other category called the category of achievable tasks. And right now I'm proposing that the category is a monodal category. The functors and the functors between monodal categories preserve this monodal structure. And in the objects in my category of achievable tasks are in fact monoidal categories, where where they have objects which provides a generating set of logical predicates or literals, and the arrows are generated by the set of actions that we can accomplish within that with the set of actions that we can accomplish. And then the tensor product is the conjunction of predicates and actions. The arrows in this category kind of mirror the same structure where they're spans, and the apex refers to some common entities between these monodal categories, and then the composition is the pullback of these span of functors. This works. The choice of monodal categories is still under exploration. So if there are any suggestions on other category options, then I'd be happy to hear them. Okay, so I've kind of laid out where I'm at with the development of this framework, and so the next steps in validating that this achieves these formal semantic requirements is first defining this functor G and actually instantiating this functor and validating that G meets the requirements of delta lenses. Checking that all of my formal semantic requirements are met in this framework. And also answering the question of whether other properties might actually be exposed just by using the structures that I had chosen. And then also identifying what other properties I should be modeling to make sure that all the aspects are captured. And in particular, what would be interesting in the application domain would be whether we can make a statement about whether an automated decision maker is more capable than another given the same information using this framework. And more capable, that would be kind of evaluated because the choice of the generating set of actions may be different for varying decision makers. And so the amount of change they might experience because the context has changed could give a hint to whether that particular decision maker is better, more equipped, or more able to do more things. And then lastly, we want to answer the question of how might we implement this framework on a computer, and what is the computational complexities of these queries. Okay. So I talked a little bit about some of my motivations and then these categorical semantics. The last thing I want to touch on is very briefly is this use of category theory in practice. Category theory, I kind of touched on a few structures that I have been using, but there is a whole domain and community exploring these formal semantics, and they, as you might be able to tell, they are flexible and adaptable in that you can add more structure, less structure in them, depending on what kind of behavior you're attempting to model. And so this is just an example list presented by David Spivak on some examples of categorical structures and their applications to a variety of domains. And then the last thing is that there is tooling and development as well, and this is done if you take a look at the Algebraic Julia CatLab repository on GitHub. Many of the all of the string diagram visualizations that you saw were developed or were rendered using the CatLab library. Okay, so thank you for listening. I appreciate any questions and feedback.
You mentioned logic several times, but I didn't actually see any logic. In my career, I've heard hundreds of lectures on modal logic, where they talk about necessity and possibility, or tense logic, or logics involving obligation, or that kind of thing. But they very seldom have any applications. You have very good applications with robot planning, but it seems to me some logic should be built into the planning, because you have to know that the action of the robot is going to be correct, so that must be a logical deduction that has to take place. But also, you need to know whether actions are possible. You know, there might be conditions, and it would turn out if you combine the conditions, you see you get into an impossible situation. So you have to be able to express those requirements somewhere or other. So at the end of your talk, you mentioned toposes, but maybe there's not a big topos, but a small topos where you can get some properties of things. In other words, embed your categories that are showing the structure of the actions into a slightly larger category, which is showing types or properties of actions. It seems to me a little bit more developed. It's there in order to be able to express that you're doing things in a feasible way. That's what I was worrying about.
Yeah, no, that's a good point, and I really think that that feeds into possibly a better choice of modeling here in this achievable task or space of task plans. I think more exploration needs to be done on my part to figure out what structures might model those like model those logical behaviors.
Where do you when you check that the category theory is doing something for you, like where does it kind of touch ground where you're like, do you more like prove these things, or do you more like make code, or like how can you tell that the category theory is touching like the thing you're trying to model? What's the interface feel like? Yeah,
I guess what I do to check that is test that by hand using small scenarios. Like if I have this idea of some behavior that should happen when I compose things, checking that when I do compose things in this setting, it achieves what I expect.
By hand?
Yeah, by hand initially. I think to evaluate it more completely, I'd have to test it against data sets, like a much larger, more concrete data set. So that's kind of where the computation ability to make this computational comes in. So I think I kind of just develop an intuition that this might work out just by testing things by hand and based on basic intuition, but yeah, it still needs to be validated.
And then how can you tell when it's like that? Like, how does the category theory help you, or like how is it kind of like what about doing it categorically feels like it's useful?
Yeah,
or
I
not,
think
or whatever?
I think that fact. So this sort of I came across the phrase of lazily evaluating things, and that sort of it resonated with me because there are properties and constructions that are afforded by structure choices with my categories that might allow me to, like, I don't have to explicitly encode every sort of composition if I can just evaluate for it at the time that I need it. And then I also don't have to describe every single map that exists between objects if I can leverage this lifting property or this guarantee of lifting to exist and kind of just enforce the constraints that are required by these lifting properties. So this way to construct new things without having to actually instantiate it all at once, and that actually captures the behavior that I want, is what I think the category theory provides to me. Yeah, was that satisfying? Okay.
Why don't we thank Angeline again?